caught it earlier.
Okay.
Okay.
Okay, so Tito, what is your role in the Septet project? What are you?
But in the Septet project, we develop, since it's divided in, we try to harvest different form of energy. My part is based on the piezoelectric harvesting and fabrication of device, at the same time material that can fit or can be more efficient for harvesting piezoelectric vibration.
Why is it important to use nanotechnology for gathering, harvesting piezoelectric vibration?
Well, it's the fact is that to study new material, and nanotechnology material has been quite reliable, has been quite robust, and we can use novel technique of growing or making those material, and a recent improvement showing what is the possibility of, in this case, for example, nanowire or nanorods to harvesting vibration and piezoelectric energy has been quite successful. There are so many papers, so it can become important from the basic science itself, and also for application to show new frontiers.
Does nanowires or coils, why do they do such a good job at harvesting piezoelectric?
But first of all, the way we grow them and the way we make them, technically we want to grow at very, very low temperature. Usually some material they have to be grown at high temperature, ceramic or those kind of material. And then plus they can coat almost any kind of surface, or it can be optimized for a specific surface. The volume to surface, surface to volume ratio is very favorable for in this case for the nanowire. And the nanowire, they tend to. The problem is that we just don't work with nanowire, with nanostructure. There are other kind of nanostructure. We started to investigate for Septet nanowire. We are going to what the structure are called nanosheets or nanoribbons. They can have much larger surface, certain flexibility that is fundamental in order to harvest more energy. Moreover, they can be tuned for certain frequency, which is fundamental also for harvesting piezo vibration.
Why is that?
But because just think about when you walk, there's not just what happens. When you walk, you move something, and that can be translated into vibration of the ground. But it's not, and the vibration are wave sound. Just a simple example, wave sounds, and those they have different frequency. Like light has different wavelengths, so they have different frequency. So based on different frequency, you can harvest or you can tune your device on each frequency. So if there is a frequency that is more common or more abundant, made by human or made by nature, there is the one that you want to harvest. And the nanowire, you can tune their size, their length, and you can tune the way they grow.
When you mentioned something, I want to go back to that it's a cold process.
It's a fairly cold process. So what we're doing for Septet, we try to stay in let's say low energy consumption. If we can grow those material with differently from other people that they grow at high temperature, and we can maintain this temperature low. At the same time, we maintain the similar or better properties, crystal properties of the material, then we gain, because to process those material would be much cheap, which goes towards renewable energy or using material for renewable energy.
I'm going to ask you to be very kind of fundamental in how you describe.
Okay.
So you are describing growing this material. Can you tell us, like, how does that work? What does that mean? But it's not like growing a plant.
I think the plant is probably the best, or the grass is the best way you can see how the nanowire grow. You seed your lawn, and then your dust, you seed it, and then you start watering, and after a while you see this grass growing and popping up, and more you water, more the grass grow. And at the beginning, the grass is very straight, so it looks like very very perpendicular to the ground, and after a while start bending, and when the wind blows, bends even more. So this is a good example how the nanowire grows. But instead of using water, we use other material. Instead of using the dust, we use another substrate, but pretty much it's the same concept.
Can you tell us what the substrate and the material is that you use?
It can be, for septum, we're trying to have as largest as possible, because the piezoelectric component is very minimal, so I have to go in places that are not used, for example, in solar panel. But so far we are being able to do on glass, so normal glass. We are able to do on metal like aluminum or like gold. And we have been showing the path, but very easily on silicon too. Silicon is pretty abundant. But glass and metal are probably the best substrates.
Okay, and let me see. So, what do these look like, and how do you know what they look like?
But
the nanowires.
We need something to stay fundamental. We need something that, if you have something that is small, you need something that can see something is small. So the best way to look at our nanowire and looking at the structural properties is the quick way is using scanning electron microscopy. The more deep way is using transmission electron microscopy. So those are optical techniques. Like you see a microscope, you have a normal microscope. In this case, it's a microscope. It's more sophisticated. We use a different light. We don't go in details, but we use a different light, and that light has a wavelength small enough that allows you to see small features. Okay, so like you see the microscope, you zoom, at a certain point you can't see anymore because there are physical limits. And in this case, we have to use a different light in order to see our material.
So can you describe what the nanowires look like?
But as I said, it looked like a little rod, or a little rod, or something like, as I said, a grass. If you look at surface of grass that is just growing, that looks more like your nanowire. They are very structured, so they have, many kids, maybe they have seen quartz. You know, the crystal of quartz that they grow and they look like, well, I think a hexagonal, depending. So they look like those one, but much smaller.
So this is really fascinating. I love the way what you're saying. I can imagine what we might cut into it visually if we can get some electron microscope images and stuff. That'd be really great. Okay, tell me about why nanowires can harvest energy.
But it's not the nanowire itself that harvests energy, and it's not particular. It's the material itself that can harvest energy. So what happens is that when material get compressed, let's think about, we have a material, we compress the material. What happens is we have across the material, we have a potential, so a force that is generated across the material. So we can use that force in order to use another form of we can storage that force in other form of energy, specifically maybe recharging a battery. Okay, so the material is nanostructured. The material is very well defined, but it's the property of the specific material that is in a nanostructured form, in a crystalline form that allowed you to harvest energy. It doesn't necessarily have to be a nanowire.
So, what are some of the problems that need to be overcome for this to be a sustainable economic?
Well, it's the efficiency, and I think it's the efficiency, first of all, and the second is the reliability of the material. Technically, they are quite reliable and they are quite robust. So, and second, I be honest, piezoelectric is not the kind of form of energy that you can harvest in order to, to have your big company like Intel want to use piezoelectric. It won't be enough, even for the university itself or for your house, to illuminating your house. It's just part of the energy that exists because it's produced every day when you walk. It's produced when the wind blows. It's produced because there is movement in some in some structures. So every time earthquake, from earthquake or vibration of the ground, so it's there, it's generated. So it can be used as a backup energy for little usage, but since it's free and it's wasted when it's not used, why not use it?
And why are you interested in this? What makes?
Well, it's a good challenge I like nanotechnology. It's a good challenge investigate what kind of nanomaterial can be most efficient. The fact is that so far I don't think there is a great efficiency, but for fundamental science, it's good to study and to show what kind of novel material can be used by the industry in the future. And it's a combination of application and a combination of fundamental research.
I'm just curious about this. We may not use it, but are there examples of nanotech material that's popular and being used now and being sold in the market?
Well, for example, carbon nanotubes are all over.
Okay.
Just a good example, probably is what the people know.
What's
more.
The advantage of the carbon nanotubes?
But there are, I mean, there are so many advantages that I don't want to even to pronounce all of them. I just make a simple example of something that a nanotube, beside its properties and optoelectronic properties, okay, think about its carbon. Okay, so any application of carbon can be used carbon nanotube. But just for example, 30 years ago they developed this technique to look. Many years ago, I think 20 years ago, IBM came out and showed some atomic structure of their material, and that was called STM technique. So then they found out a technique that is AFM technique that works in a